Hello fellow problem solvers. So they're going to be doing a problem from the JBMO shortlist of 2017, problem number G3. This is my problem proposal, probably one of my favorite G creations that I ever made. Probably the favorite geometry problem I ever made. And I'm biased, but I believe this problem is absolutely beautiful. And I invite you to try it out for a minimum of 30 minutes. Ideally an hour to 2 hours, not more than 4.5 hours. Though even if you do 4.5 hours, I really like this problem. Try to find two different types of solutions because this problem has really different ways of thinking that you can apply here. So now without further ado, if you'd like to go along with us, give this a shot for the next 15 minutes. Put your first ideas out on paper. Read this wonderful creation of mine as far as I'm concerned. And now without further ado, let's begin. So what do we have? Consider a triangle ABC such that this is true, D is on BC, and E is on, this is on the arc, this is on the side. Bad is CAE is less than half of BAC. If S is the midpoint, prove. And if this holds true, prove this is true. Okay, so let's see. AB is less than or equal to AC. So let's actually draw this circle. What do we have? We have doo-doom, 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 A, B, C. And we have points. So E is here. CAE is less than half of this. So let's put E here such that this angle is equal to this angle, D. These two angles are the same. Boom, boom. And the angle ADE, so this is beta, this is gamma, this is beta minus gamma. And if we take the midpoint of this, call this S, that this angle is twice the size of BAC. Okay, so there are a couple of ways to go about this problem. And I'm going to present those different ways of thinking here. One way of thinking goes, wait a second. Where else can I get the angle beta minus gamma? Or one just like asks that. Another way of thinking says, wait, what do I have from this being, what happens when I have these angles, right? I have this as gamma, and because this whole thing is beta, then this is gamma as well. And if I call this angle X, X, I have this angle right here is also X. This is alpha minus X. So with this, and this whole thing is alpha minus 2X. So now with these couple of ideas, I also actually have one more idea. The other one is how many pairs of points D and E could actually satisfy this relationship such that this is a fixed angle and that these two are equal. You know, what happens when E and D are moving from here to this, how many times can they form this angle at two different places? So those are literally the three different approaches which lead you down three different solutions. Again, why I love my problem. So now, if I invite you to pause if you didn't come up with any of these approaches, pick one and push the problem further for the next 15 to 25 minutes. And now let's take it further. So I'm going to first start off with the idea, what do I have from the angle? So there's the most simplistic kind of idea. And see, okay, also just this is equal to this. And I have gamma X, I have gamma X. So this is the point E. So I have AEC, triangle AEC, is similar because this is X, this angle gamma. So A is where X is, C is where X is here. C, the triangle C, E, so CE again, and D. And what does this give me? Well, it gives me that. And do I also have that anywhere else? I also have this is similar to this triangle right here. So let's write down this similarity as well. This is similar to triangle. I have X, I have gamma. So I'm looking at X, AEC, ABD. Now, this similarity holds true. You know, we need to see when does the similarity hold true. Is it something specific about this angle or about this angle condition? And this similarity holds true only because these are X. though the CED similarity holds true only because this is beta minus gamma. So that, and that this is x, but that is important to take note. Why does a similarity hold true? How are we using this fact? Okay. So now what do we have from this similarity? AEC, and because we're taking, say, this midpoint, we might be interested in these similarities simply because I'm going to take the midpoint of AD here, and that's the same as the midpoint of CD here. And then that might give me an angle, like I might get BSD. Actually, it's not that I might get it, I have the angle BSD is equal to the angle E, this midpoint, and actually BSD, this is gamma, so it's equal to this one. Yeah, it seems like it's equal to this one right here. And yeah, because this is beta alpha minus x, okay, so it's equal to, so the midpoint, so this would be equal to this one. And it's important just to like keep track of these things. And then the other midpoint would have, if we took this other thing, this other midpoint, then we'd have this other angle, right? This angle would be equal to this one. And then this plus this, we would need to prove that it's equal to alpha. Or in other words, we need to prove that this is a 180 minus alpha, because this one already is 180 minus alpha. And with that, because this is parallel to, actually, we yet don't know what will happen. We yet don't know what would happen here. But this is parallel to this. This is this should be 180 minus alpha, which means this angle should be equal to this angle. And there are only two such points E on this side which satisfy that, right? The foot of the perpendicular from D here and the midpoint of BC. You see, this is one way of thinking. That leads you to what E could potentially be. But let's see what we have from the similarities. So let's take the AB. Let's take first AEC. So we have AE over CE is equal to, what's it called? AE is equal to CE. I take CE over ED. So now what does this give me? It gives me AE times ED is EC squared. Have I used anything specific about E here? Not, I mean, have I used what I want to say? Have I used anything about A or C here? Because due to the symmetry we have in the problem, we also have the triangle AEB is similar to the triangle BED, right? AEB, beta alpha minus x, and the other one is, say, alpha minus, like, let me just double check where it is. So BED is this, and we have, actually, wait a second, so we have alpha minus x is B. Oh, wait a second, maybe we don't have this immediately, where there's not as much symmetry as I thought there was. This is beta. This angle is beta. Oh yeah, this is alpha minus x. Yes, there is symmetry. There is symmetry, BED. There is that symmetry as well. So on the other hand, from here, we would get that AE over BE is equal to EB over ED. Now, AE times ED is EB squared is equal to EC squared. And so EB is equal to EC, which forces E to be the midpoint of BC. And now further continuing this like search for similarity, we see S is here the midpoint of AD. So we want a similar triangle which has AD in it. And we say take this one and CED. And then we know that if we take the midpoint here of this side, right here, we'll have that this angle is equal to this angle due to these similarities, right? Because this is the corresponding midpoint. The midpoint of CD corresponds to AD in this similarity. You can also prove it by this over this is equal to this over this times a half, which is this over this times a half, which is this over this. You have the angle here. This angle is equal to, actually, wait a second, I'm wrong. This over this is this over this, and then you have this angle as well. Same angle. So what do we have if we take the midpoint here of CD, call this midpoint, actually let me draw a diagram. So we have boom, boom, bam. I have this reflected here, boom, E, D, C, A, B. I take this midpoint, this is X, this is X, this is the big angle. So it's the same as if I took this midpoint, boom, and I have this angle right here needs to equal this angle right here. And what is this angle right here equal to? Well, we'll find out. But now the problem quickly falls apart because this angle here, and on the other hand, actually, we just take this midpoint is equal to, when you take a midpoint here, this angle right here. And now this plus this is equal to what? We need to show that it's equal to 2 alpha. But we have this 180 minus alpha. And because this is the midpoint, this is the midpoint, this is the midpoint, this is parallel to this is parallel to this, so this is a parallelogram. So this is 180 minus alpha, and so both of these are alpha, and this is 2 alpha. And that finishes up the problem. And this is, one way of thinking. I have the angles, what do I do with them? Now another way of thinking is, where do I get the beta minus gamma? And now we'll clear up the diagram, the board, and go down that route. And I invite you, if you didn't go down this route, if you wanted to go down this route, which I think is cooler, I invite you now pause for another 10 to 15 minutes and try to just go down this route. Forget about the similarity here. Go down this route for now. And now let's do that. So now we have this angle is beta minus gamma. And the question is, where else can I make beta minus gamma? Where else do I have it? There are 2 answers to this question. One answer is I can intersect this with the circumcircle, and I'll get this is beta minus gamma. If this point here, call it F, then I'll have the angle on AF is beta minus gamma. So this is beta minus gamma. So it means this angle here is beta, which means BF is AC, FC is AB. So this is parallel to this. Or also like this 180 minus beta, this is beta. We have AF is parallel to BC. So that means that every single pair of these points needs to pass through F. However, if you take 2 different pairs which have this same angle condition, like this, and you intersect them, they intersect internally. So it means there's a unique point, there's our unique points E and D, such that this whole thing is true. And that's one place where beta minus gamma occurs. You can go down this route. Or you can say, wait a second, I have beta minus gamma. Let me just clear this up. I have beta minus gamma. Where could I also put it? And the answer is, well, if I put it here on this side, if this is beta minus gamma, this angle is gamma, i.e. this is the tangent to the circumcircle. And mind you, like first of all, this is the tangent to the circumcircle. And now this is then beta minus gamma. And this is a cool point. It's a cool, well-known point that we have something for. And I mind you, not only that, but also TA is also tangent to this circumcircle, because this is now gamma plus X. And this is gamma plus X. So it seems like we have some cool properties that hold for E and D as well here. Now, what are you going to do in this picture? I invite you to pause for 10 to 15 minutes and try to push the problem further. And here's the next cool step. And the answer is, well, you also mind you have these 4 points. A, T, E, D are concyclic. So this angle right here is equal to this one, which is equal to gamma plus X. Now, also, this angle right here is equal to gamma plus X is equal to this one. And where else do you have gamma plus X? Well, if you take this angle right here, you'll have this is gamma plus x is equal to this angle. Amazing, amazing. Or you can also look at it as this angle here is gamma, and because of the concyclic points, this angle right here is x. So I have now TB times TC is TD squared is TA squared. Isn't that rad? And now, let me ask you this. So T is the tangent, so D is the point of tangency to the circumcircle where you have T, when you have T as well. And now what happens to O? I mean, what happens to the midpoint actually is the point. And the point is, if this is S, how do you define really a midpoint? Right, you can define a midpoint of a sort of chord by taking the circumcenter and getting like a 90-degree angle on it. Now, it's also true because TA is TD that TS is also perpendicular to AD. So TSO are collinear. And now what do you do? Please pause for 5 minutes. Now what do you do? And the answer is, well, look at this, because this is a tangent, right? TA is a tangent. So OAT is 90. And now OAT is 90. Mind you, we have to prove that BSC is BOC. So we have to prove really that TS times TO is TB times TC by power of point. And how can we prove that? Well, we have TB times TC is TA squared, looking at it backwards. So we need to have TS times TO is TA squared. Going forwards, is it? And the answer is yes, because this is 90 and this is 90. So you can say you have similarity, a right triangle, and a foot of perpendicular. So TS times TO is TA squared, which we know is equal to, the way we constructed T, is equal to TB times TC. Right, and we know TA is TD squared from the other concyclic points. And now, from TS times TO is TB times TC, it follows that BSOC are concyclic, and so the angle BSC is equal to the angle BOC, which we know is equal to 2 times the angle BAC, and so we are done. This is a big point why I'm proud of this problem. Really, like, you construct this line intersecting with BC, so you get beta minus gamma, and then things just fall into place. Oh my God, look at that. I'm excited, obviously. So this is the second sort of solution. This is like the first official solution I wrote in the packet because I thought that this solution was absolutely rad, beautiful, yay. And now we can go back to our final solution, which is looking at, okay, how many unique points? There's one unique pair D and E because of this point here, F, because that point is AF parallel to BC, and that argument. So how are we going to figure what this point is, right? How are you going to figure out what are these points? And the answer to that is, I invite you to pause for 5 to 10 minutes and see if there's a different argument you can get to here. Mind you, I needed to come up with these different arguments to sort of sell the problem to the committee. And the answer is, so what do? We say, okay, take F, take E, the midpoint of BC, take this point P, such that when this point, D, such that we intersect it, FE, we get, with the circumcircle, we get D, and intersect this at Q. Now we say AF is parallel to BC, so this is an isosceles trapezoid because these four are on the circumcircle. So now what does that give us? Because it's an isosceles trapezoid, that means that, if O is their center, OA is OF, and OM is the perpendicular bisector of BC, and because these are, these four parallel, so this is also the perpendicular bisector of AF. So, and because M lies on there, MA is equal to MF. And from there we have this angle is equal to this angle, and also then this angle is equal to this angle. So we have, not M, I'm saying M instead of E. ED is EQ, EF is EA, because this is equal to this, we have this is equal to this due to the angles. And now, what does that give us? It gives us that because these two things, because this is parallel to this then, right? Because if these angles are the same, actually, why is this parallel to this, I should say? Because now this is equal to this. So, what's it called? When I take the perpendicular bisector here, actually, let me double check, like, why is this now parallel? Well, AF is parallel to BC. So we have this angle is equal to this angle is equal to this one. So we have DQ is parallel to BC. And now we have CQ is BD. And so the angle BAD is CAQ, which is CAE. And so these are the points which satisfy this relationship. And both of these are less than half of BAC because the, what's it called? Because this is the midpoint and the angle bisector goes through here. Like there's an argument to be made there, but it doesn't have, like it's sort of, at this point, I think it's obvious-ish, I would say. It really depends on the level of competition. I think at a JBMO, you could just say this. And now on this problem, because that's not the biggest claim of the problem. And now what happens is, okay, these are the same. I have, let me take the circumcenter O. And now I know that this is the bisector of these sides. So this is also an isosceles triangle. And then these points meet over here at some point down there. Now I invite you to pause for the next 10 minutes and try to push the problem further. And here's the next step. Well, the next step is call this point now X. And remember, we're going to take O and a perpendicular here. So we're going to have a couple of things. One is if we now actually call this point what it is, this intersection of AD. Let's call this point, what do I have? Say Z. I don't have Z yet. This intersection is X. I have that Z, so what do I, first, like, what is it that I have from here now? I have that, I need to prove that these 4 points are concyclic. And that is what I intend to prove. So now, first question is, what do I have for this point now? X. And the answer is, why do I intersect these? I intersect these because now I can use some facts. And some of the facts that I can use is that you see this angle is equal to this one, is equal to this one, is equal to this one. This is the angle on the chord FQ. So this angle is twice the angle on the chord FQ. So FOQ is also equal to this angle. So I have that O, F, Q, and E are concyclic. I have these 4 along the circle. And now via power of point, I have that this times this is equal to this times this is equal to this times this. So let me actually write that down. XO times XE is equal to XQ times XF, which is equal to XD times XA, because it's now the power of point with respect to this circle. So these points are also concyclic. Now, another thing is because this is a 90-degree angle and this is a 90-degree angle, O, E, what's it called, Z, and OSZ are both 90. So these 4 points are on the same circle. And then I have that this, what's it called, XO times XE, this times this is also equal to XZ times XS. So I have this times this times this is the same as this times this. So I have these 4 points are also going to be concyclic. And now, what do I also have? I am going to actually invite you here to look at these powers of points and try to, like, if you don't have a lot of practice with power of point, I think this is a good sort of place to see how it works. And I would invite you to pause for, say, 10, maybe 20 minutes if you don't have any practice with power of point, and see what is it that you get when you, when you make these intersections here and here. This point X, call this point O. So what do you get from the power of point? E, Q, S, and I called this Z. So what do you get? You get, like, just pause now and try to push it forward. And the answer is, so you get now, you have this times this is equal to this times this, which gives you that these 4 points, Z, Q, F, S, are concyclic. And then what? What do we have then is a question. We should also have the same on the other side. And now let's think about this. So we have this angle condition, and given these are concyclic, do they lie on any intersection of anything cool or interesting is the question now. And the answer is I do not see anything very cool or interesting right now to begin with. So let's continue on. And the next sort of thing is, next step is that, well, mind you, you have this angle is equal to this one due to this, this being a side bisector of AF, right? The segment bisector of AF. So you also have this angle is equal to this one, like OXA, OXQ are equal. Now you also have OA is equal to OQ. Does that remind you of anything? And the answer is there's a dilemma with the angle bisector and the side bisector intersect on the circumcircle. So the points OAQX are concyclic. And now from those concyclic points, what do you have? You have the power of point with respect to E. You get EA times, so EA times EQ is equal to that EO times EX on one hand. And on the other hand, this is equal to EB times EC. So we have EB times EC is EO times EX. So we have OBCX are concyclic. And now, what is enough for us to prove? Well, if we can't get to OSB are concyclic directly, by power of point, we don't have that yet. But can we prove that BSCX are concyclic via power of point? What would be enough? Well, what would be enough is for us to prove that ZS times ZX is ZB times ZC. But that's what's enough for us to prove. Now, given we already have, we have ZB times ZC is ZA times ZD. So what's enough for us to prove is that ZD times ZA is equal to ZS times ZX. And what do we have for the points ZX? What do we have for these 1, 2, 3, 4, 5 points? And the answer is, and this is a more of a useful lemma that I saw that can be used, and it's a bit of a stretch to think that somebody on the junior bulk math could use it, but I wanted to introduce you to this solution as well. Because what you get is, you call this segment, say, of length, call this of length X, call this of length Y, Z, and T. Now, mind you, S is the midpoint of AD, so T is actually Y plus Z. Now, what is the power of point? Here, XD times XA, XD times XA, that's equal to small x times x plus y plus z times 2. And this is equal to, we've shown that this is equal to xz what's it called, xz times xs. So xz times xs is x plus y times x plus y plus z. So we have this. And that's what this power of point gives us. The thing we need to have this. So what's it called? Zs, which is of length z, times zx, which is of length y plus x. We need this times this to be equal to, this is a question mark, is it equal to y times z, so it's like y times 2z plus y. We need this to be equal. And from here, what do we get? We get x squared plus 2xy plus 2yz is equal to x, so this is x plus y squared, which is x squared plus y squared plus 2xy, and then x plus y times z plus xz plus yz. Now the x squared cancels out, xy cancels out, yz and one of the yz's gets left, and we get this equivalent to yz is equal to y squared plus x times z. If I'm not mistaken, I think that is about it. This is what this power of point gets transformed into. Now, what does this one get transformed into? Well, this one is equivalent to zy plus zx is equal to 2yz plus y squared. And then this is, we cancel these out, and this equivalent to zx is yz plus y squared. Z. Okay, so I might have messed up the calculations somewhere. These two things should follow from one another. I might have where did I mess up the calculation? Y squared on this side. What's it called? Is it yz here? Actually, there's no, it's not y. My bad. This is supposed to be, this is not, what's it called? 2 times yz, this is 2 times xz. Now xz gets canceled out here and here, and we get, what's it called? Yz remains here. So actually this is yz, this is xz, and now these two things are equivalent. So this condition is equivalent to this one, which means if we have this power of point right now, that this times this is equal to this times this, given s is the midpoint, that implies that this times this is equal to this times this, which then gives us, what's it called? It gives us zb times zc. We know it's equal to zd times za, but that is equal to zs times zx, so these 4 points are concyclic. And because these 4 are concyclic, these 4 are concyclic, then the point, that is the same as saying S lies on the circumcircle around BXC, O lies on the circumcircle around BXC, so O and S lie on the same circumcircle around BCX, and so this is equal to 2 alpha. And this finishes up our problem. The last solution I get, now I see that this maybe was a little bit of a downer because it's not as cool as the second one, which is, woo, what's happening? But this is my favorite geometry problem I ever made. And this finishes it up. And the way I made it, I'll tell you that as well. The way I made the problem was I was doing a problem from the JBMO, which had a thing which had this condition, right? It had the condition that these two angles are equal. And then I thought to myself, okay, wait a second. When I realized when I have the midpoint, this is where the median line meets the circumcircle, and I knew that this angle was equal, that I knew that this was gamma and this was gamma as well. So I knew this angle was beta minus gamma. And it was just like a wonder to me, like, does this uniquely define the midpoint and this other point where the median line meets the circumcircle? And I thought it would be so cool if it does, because when you have two floating, points which are floating like this on the line and the circumcircle, with a condition that connects them, if that's unique, that's pretty hard. That's a hard find. It's hard to find that these are actually unique points. And I thought, okay, it actually is unique. This uniquely defines the midpoint and the side median line. And then I thought, okay, how can I make this into a problem? I can't just say like, oh, prove this is the midpoint. Then it's like not as interesting. So I added the condition. I knew that the midpoint of this slide lay on the circumcircle around BOC. So I thought, okay, that'll be the problem, right? And you have to, and then I saw, okay, how can I solve it in many different ways? And I saw, okay, wait, with similarity, I can just like find this as the midpoint, which was one cool idea. And then the other cool was like, wait, if I had this is beta minus gamma, what happens if I take this, where the tangents to A meets BC? And I knew that if I took this tangent and the tangent from here, they meet on BC. So I was like, maybe I can prove if I take this tangent, that this is a tangent. And I saw, oh, it's beta minus gamma, so I probably might have something good. And when I saw that, I was like, that's the problem. That's when I actually really started to love this problem. And this finishes it up. And as always, thanks for problem solving.